Well, good evening, everyone. And the slides are shown here. Sorry, just let me find myself now. Good. I want to talk about the FlexiArch tonight, and thank you very much indeed for coming along. The FlexiArch is not a new type of arch, but it revolutionises arch construction. And this allows arches to be built more quickly and less expensively. In the past, arches were very, very popular, and unfortunately they became very expensive, and for that reason they were abandoned. So at present, if we want an arch structure for aesthetic reasons, we have to use a reinforced concrete arch. But unfortunately, because there's reinforcement in them, they are not long lasting. So the future lies with the FlexiArch. I patented the system about 10-15 years ago at Queen's, and it was licensed to Macrete. Over 70 bridges have been built all over the United Kingdom and Ireland, and a senior bridge engineer at Network Rail has said it's the most significant advance in arch construction since 1900. And users, and I'll not use ecstatic here, are very happy with the system. Going to the Shenton Bridge here, there was a bridge over a tributary of the Severn in Shropshire, and it was a 3-span masonry arch, and there was severe flooding, and it was washed away. So the Shropshire County Council decided to replace it with a 14-metre span FlexiArch. Now, the only way to really understand how the FlexiArch works is to see a video of it in operation. So this short video here shows that as you lift it in the crane, it bends into the shape of an arch. And when you lift it clear of the lorry, it forms into the shape of an arch, so that, in fact, you don't need any centering, and this speeds up the construction dramatically. So these units are then, in this particular case, weighed about 14 tonne, so they're not modest weight, and this span was 14 metres, and these were lowered gently into position and allowed these units to actually bed in to a very, very precisely located unit. The actual bridges have been in spans from 4 metres up to 16 metres, and these are dropped into position, and the Macrete decided in this particular case to also produce precast spandrel walls. These spandrel walls were specially prepared so that the structure there, you could actually put stonework on it to make it look like a real natural arch. And in this particular case, the clients wanted a brick finish, so that's what we provided. So the FlexiArch system, in summary, is a high-quality precast concrete, and the big advantage is it has no reinforcement that corrodes. There's no need for bearings. It's manufactured in flat-pack form for delivery to site and for storage in the factory. You can stack one unit on the top of the other, and can be installed in hours, not in months. So the FlexiArch system is aesthetic, it's strong, it's durable, and it's maintenance free, just like a conventional arch. And just to bring you to your mind, some Roman arches over 2,000 years old are still in service. So why are we not using more FlexiArches? So thank you very much indeed for your attention.
Adrian, ladies and gentlemen. The final time was 230 seconds.
Adrian,
yes.
Thank you very much. I've long been a fan of the FlexiArch, and I suppose I'm going to ask you your own question back. Why are we not using more FlexiArch bridges? What is the problem that we cannot get these out and about and in use? Because you just immediately see a solution to problems all over the world.
Well, this was one of the reasons why I decided to enter this competition, to force myself to put it in something short and to the point. a lot of people don't know about it, but they don't like using new things. And because it's new, they don't use it because they like somebody else to try it out first. But we're very fortunate here in Macrete. I was very fortunate that I went to Macrete and asked them if they would make it. It turned out they were the biggest manufacturers of arch bridges in the United Kingdom and Ireland. And it turned out I couldn't have gone to a better group. And they adopted it, and 70 bridges is not too bad, about 10 bridges a year nearly, and it's getting more and more as it's going on. And there's quite a few examples here in Northern Ireland and across the country.
Okay, thank you.
Can I just let Rory know? I think Emer's been reading my handwriting. That was my question. My only other question is there a possible financial reason or safety reason that it's not being used more?
It's cheaper and it's quicker. So there's not. It's just purely, people just do not like adopting a new system. And that's a huge battle, and that's one of the reasons why it was useful to have this thought of a quick 200-second pitch, which went a wee bit longer than 230 seconds.
In principle.
I think you started your clock early. Sorry, I couldn't resist that.
Would you mind explaining to us all exactly how the components are joined?
Yes, that's the secret. There was an engineer in Glasgow who worked all his life trying to develop a flexible arch system so that you don't need centering. Normal bridges need centering, and then you build your stones up on the top, and then you put your keystone in. So Gordon Millington was coming back on the plane from a meeting in the Institution of Civils in London, and he said to me, well, why do people not use arches more? Because they're the best structure you can get. And that was fine. I set about, and quite a few students did projects in Queen's, and eventually we got it patented. And what it does is, the guy in Glasgow had produced a system where it was very, very complicated, and it cost more than a normal arch. So the whole secret is to get it so that it in fact costs less than a normal arch. And there's a special reinforcement that's put in which is not corrodable.
Top secret, then?
It's not that secret. It's very simple. That's why they've been using it.
Thanks very much.
Thank you.
Any questions from the audience? Make yourself known.
There's been a lot of talk about a bridge between Northern Ireland and Scotland. Would this be feasible to use as arches to span that 18 miles?
No. No, the maximum span we could go to would be probably up to 100 foot or 30 metres. But I had a student whose brother actually works for the BBC, Will Leach, and he did a project on a bridge or a tunnel across to Scotland. And at that time, the Channel Tunnel was struggling to pay its way. And the population in Europe's hundreds of millions, and the population in England is 50 or 60 million. How could we ever make it economically viable? There was no chance. It would have cost more than a channel tunnel, and it just is not on. It's one of these ideas that some brilliant architect has come up with, but it doesn't make sense. It is not economic. It would cost millions and billions. The channel tunnel was very, very expensive. So I'm afraid it's a nice talking point, but it doesn't really make sense. Sorry, I couldn't resist that. Sorry? Yeah, well, when you actually look at the economics of it, if you can't make it pay for 8 million people going across to 60 million, and they can't make it pay for 60 million going to 400 million, no way. And the geology is so difficult.
To scale it down a bit, Adrian, would it work at narrow water?
Not really. I don't know what the span is in narrow water, but we can get these. One student did a project actually with me, and he reckoned he could go up to 60 odd metres. The biggest problem is when you have 60 metre span, you need one hell of a long lorry. But we've now designed a system which you can actually interconnect them and joints in sight, a dry joint in sight. So it allows us to do that.
Anybody else? Yep, down the back.
That's fine. Is there any more advancement in actually to use a different material than concrete?
Yes, you could. It's patented so that you could use another material apart from for timber. You could use, for example. The only problem with timber is that when it's out on site, it tends to deform, and concrete tends to keep its shape better. And the big advantage is the quality of the concrete that we can use is 60 Newton per square millimetre or 50 Newton per square millimetre, whereas ordinary masonry, you're lucky if you can get 10 newtons per square millimetre out of it. So it's a lot better. It's a better material. It's a better bridge than you get with a masonry bridge. And the big advantage of precast concrete is that you can make it the exact shape you want.
Adrian, you mentioned that you came up with this concept, and it sounds like you've done a lot of research with a lot of students over many years. But can you think back? Was there a eureka moment whenever you thought, "Oh my goodness, this is going to work"?
The interesting thing that you find these things out. You put a patent in, and we had a patent in the United States and Canada, and we had patented in Europe. We struggled to get it patented in Europe because I think the guy had a vested interest in probably stealing the idea, but it didn't work out. But we found out that someone had patented almost exactly the same thing in 1913 in North America. But fortunately, there was two ways of constructing it. One was using precast, and the other was to use cast in situ. And in this particular case, the one that we'd selected was the one that he hadn't worked on. He could never get it to work, and it didn't work, and he challenged it, but we managed to defeat him in that. So the idea, the guy in Scotland came across, and he said, that's a simple way of doing it, and that's why it's cheaper. But he had come up with this very, very sophisticated system of doing it, which cost a lot more. Sorry, hard to see the audience in the back here.
Adrian Long, one more time, ladies and gentlemen.